graphs that we're going to look at. The first one is the exponential graph. You'll remember this graph from last year. It will have an equation that is in the form y equals a to the power of x. A will be a base number, so like for example y equals 2 to the power of x, or 3 to the power of x, or 4 to the power of x, which are the ones that we're going to look at down here. Notice that the x is the power or exponent. Exponential graphs have one horizontal asymptote, which you will remember to label on your graph. An asymptote is a line that the curve approaches, which means it's getting closer and closer to that line, but it will never reach it or touch it. Okay, so we're going to fill in our table of values to draw 3 exponential graphs. So on your calculators, we type in 2 to the power of negative 3, doing this equation first. 2 to the power of negative 3? 125. Yep, 0.125. 0 to the power of negative 2?
0.25.
0 to the power of negative 1? Yep. 2 to the power of 0?
1.
2 to the power of 1?
2.
2 to the power of 2?
4.
And 2 to the power of 3?
8.
Good job. Let's fill in the whole table while we're at it, okay? So let's just change the base to a 3. 3 to the power of negative 3?
0.037.
Yeah, I'm just going to round that to 0.04. We can't really sketch that accurately anyway. 3 to the power of negative 2? Yep, so 0.1 will be fine. 3 to the power of negative 1? 0.3 repeater, or just 0.3. I'm just doing one decimal place there. 3 to the power of 0?
1.
3 to the power of 1? 3 to the power of 2?
9.
And 3 to the power of 3.
27.
This is the easy part, isn't it? So 4 now. 4 to the power of negative 3. I think...
0.02.
Yeah, we'll round that one up. 4 to the power of negative 2.
0.06.
Yeah. 4 to the power of negative 1. 4 to the power of 0.
1.
4 to the power of 1. 4 to the power of 2. 4 to the power of 3. It's a race. Wonderful. I'm sure you'll be also fast with your exercises.
Very.
Okay, let's plot those. So the Cartesian plane that you've been provided, the axis is already on there for you. We don't need anything below that x-axis. Our x values are 1, 2, 3. I'm going to space it every second one just to help spread it out a little bit. And going to the left, negative 1, negative 2, negative 3. Now, the values in our table will go up to 64. But if I space it out that much, it's actually going to make everything crammed together a bit tight. So instead, I'm actually going to leave off the 3. I'm going to take the 16 as I'm going to leave off this column. I'm not going to sketch that one. So I'm going to take 16 as my highest value. And that way I can just go by ones on that vertical axis, which will spread it out more nicely. 1, 2, 3. Perfect. So plotting, yeah, so obviously it's very hard to plot 0.125. It's just a very small value way down here, very close to the axis. Make sure it's not touching. At minus, I'm going to, yeah. At minus 2, we have 0.25, so it's coming up to about a quarter. Then we're at half. 0 is 1, 1 is 2, 2 is 4. We can fit the next one for this one. 3 is 8. That one does fit. So very carefully draw your exponential curve. Make sure that as you're coming down to that really, really small part, that your curve does not look like it starts to bend back up. Mine almost does. Maybe I should fix that. Because if you do that, you could actually lose marks in your HSC because they may think that you've gone, oh, I don't actually know that that is going to keep going down. They don't want it to look like it might curve up like a parabola. Okay, make sure it looks like it's going to keep going down. While we're here, let's draw on our horizontal asymptote, which is that x-axis. So I'm going to make my red pen nice and big so you can see it. So we draw dots across our axes there to indicate that that is an asymptote. My graph is coming down really, really close to it but won't touch it. We write the equation of that asymptote next to the line. So that's a horizontal asymptote, HA, the horizontal asymptote. And we want the equation of it. It's going through the y-axis, so it's y equals 0. And all of these ones are going to have that same horizontal asymptote. Let's draw the second one. What colour will I use this time? Green. So our value starts really small again. We're down really, really tiny. It's going to come up a tiny bit. It's still below. It's actually below the other graph at this point. 0.3, it's still below the other graph. When we get to 1, they go through all these graphs go through y equals 1. And then all of a sudden it's getting steeper than the other one. At 2, we are at 9. So it starts off smaller, and if you can try to squeeze in your next graph below the first one, then it goes through the 1, and then it is steeper on the right-hand side. Exponentially increasing, Ashton. Yeah. Last graph. Again, this one's even smaller. Do you think you can squeeze another one below that one?
No.
Probably not. We'll do our best. I think I need a different colour. Let's go orange. All right, so just below, smaller again. Technically, they really should not be touching your axes. They all go through the 1, and then it's going to be steeper on the right-hand side. You don't normally draw this many graphs on the one Cartesian plane, so you're not usually battling for space. But you want to see that little trend. You want to see that the bigger the base number, the smaller it is on this left-hand side. Okay, so as my base number increased, it got smaller and smaller on this side. It was below each time. But then on the right-hand side, the bigger the number is, the faster it increases, so it gets extra steep, extra fast on the right-hand side.
So if the base number was like 1,000, it would still never touch the 0.
It would never touch, technically.
It
would get so close.
But if you put in the calculator, what would it say?
It'd probably give you an error because it can't do too small. All right, next page. A rectangular hyperbola. This is our second type of graph that has asymptotes. This type of graph will have the equation y is equal to a over x. Again, a is just a number. Or sometimes they rearrange it to be xy equals a, xy equals number. Now on the end there that says a cannot be equal to 0. Okay, because if I had 0 on the top of there, 0 divided by anything is just 0, it would no longer be a hyperbola, it would be back to a horizontal line actually. Okay? Hyperbolas will always have 2 asymptotes. One will be horizontal and the other will of course be vertical. And again, there's a reminder there that an asymptote will get closer and closer but will never touch. So let's complete the table. For our very, very most basic hyperbola, y is equal to 1 over x. So subbing in minus 3. 1 over minus 3 is minus a third or minus 0.333. I'm just going to leave it as a fraction. Easier. Subbing in minus 2, they'll get minus a half. Subbing in minus 1. 1 over minus 1 is minus 1. 1 divided by minus a half is going to be negative 2. 1 divided by negative 0.25 is negative 4. So I've deliberately put in a few extra values in there so that we can see the shape of the hyperbola better. If we just go from negative 1 straight to the 0, you don't actually see the hyperbola bend very much. So we put a few extra decimals in there. Thanks, Ashton. That's enough. You don't need to do that every lesson. The 0 is an important point. If I try to sub in 0, I have 1 divided by 0, which is impossible, and that is where one of our asymptotes is. So yeah, we put a star or a dash or something in there to indicate there's no value for that one. Then on the other side, these are somewhat symmetrical. If I sub in 0.25, 1 divided by 0.25 is 4, 1 divided by 0.5 is 2, 1 divided by 1 is 1, 1 divided by 2 is a half, and 1 divided by 3 is a third. So same values as before, but they're all positive because I don't have that minus sign in there. So sketching that, we are just going to be using a scale of 1 for both the x-axis and the y-axis. Let's put our asymptotes on there first. I know I have a vertical asymptote at x equals 0. So we put VA for vertical asymptote. It's going through the x-axis, so it's x equals 0. The other asymptote that we're never going to get to is going to be the y equals 0, 1 as before. So horizontal asymptote y equals 0. Plotting my points. At -3, I'm at a third. -2 is a half. -1 is, whoops, I should be in the minus side. Thank you. Minus, and then -1, minus a half is -2, minus a quarter is -4. Then we've reached our asymptote. That's what we call a discontinuous point. Then we jump over to the other side. So at 0.25, we're way up at 4. At half, we're at 2. Then 1, 1, 2, half, 3, third. So we call that a rectangular hyperbola because my two asymptotes are meeting at a right angle. There are actually graphs out there where they do have sloping asymptotes, but fortunately for you guys, you're not going to have to learn them yet. The advanced people might have, the extension people will maybe dabble in that a little bit. So there is our basic hyperbola. Then we're going to have some questions that talk about variation. And there's two key words that you're going to have to look out for. The first word is direct. So direct variation is a variation where y varies directly with the x. However, it won't always be x and y. These are going to be more practical questions often. You might be relating area with a capacity kind of thing. You could be using other letters in there. But it will have the basic form of y is equal to kx. So the y equals x part, that's your normal straight line. The k is just indicating different gradients. You would have a number that we're going to be finding to put in there. Okay, so direct variation is talking about a linear relationship between the two variables that you've been given, and it will be in that form, where it says there that k is the constant of proportionality, which we will be finding. The other type of variation is inverse variation. So you'll see, it'll say something in the question that such and such varies inversely. You'll be looking out for that key word, inversely. And that will indicate that you need an equation in this form. Y is equal to k over x, which is the hyperbola that we were just looking at. That is a type of inverse variation. Again, k is the constant of tells you the steepness of that curve that we will have to determine on a case-by-case scenario. All right, so example time. For some reason, we're starting at number 3. The amount of paint in litres used to paint a building is directly proportional. So that's what I'm talking about. There's that word, key word you've got to look out for. Directly proportional to the area A in square metres to be covered. Write this algebraically. Now, we're not using x and y. We have been given other symbols. We've been given P for paint and A for the area. Okay? So our paint P for paint is directly proportional to the A, and we know that we're going to have some constant of proportionality in there that we are going to have to find. That is what that is saying as an equation written algebraically. That's part A done. Part B gives us more information. A certain building requires 48 litres of paint, that's the P, that's the paint, to cover an area of 576 metres squared, that's the A. Find the constant of proportionality, find that K, and graph the function. So subbing those numbers into the equation that we found in part A, we would get 48 for the P equals K, I don't know yet, but the A is 576. To get the K by itself, we're just going to divide the 576 across to the other side. So 48 divided by 576 is 1 over 12. That means I now have a complete relationship between P and A. The equation for P is going to be equal to, instead of K, K is 1 over 12 times A. You could also write that as A over 12.
What is K?
K stands for the constant of proportionality, because each directly proportional question is going to have a different slope for that graph. So you've always got to find that constant first, so you know how to use it. You can use that for the rest of the question. We need to draw that. Now remember that directly proportional, these are going to be straight lines. That's a straight line. A is where my x normally is. So on my Cartesian plane, my A is going to be on the horizontal axis. And my P is the y, what is normally the y value. Now sketching a straight line, we have lots of different strategies. That one there, I could probably just use the y equals mx plus b form. Okay, so the y-intercept for this graph would be 0 because there's nothing added on the end. So it's going to go through the origin, which makes sense. You don't need any paint to paint no area, right? Then we use our gradient. So the gradient is the 1 over 12, which means I want to rise 1 and run 12. So rising 1 and running 12 to the positive side would be a point over here. And we can connect that up.
If you want to paint negative area, would you need negative paint?
Which is why, because this is a practical question, you would not extend. I'm actually going to stop that at the origin, because in reality, you can't have a negative area and negative paint. So we're just going to stop at 0. Okay, so 0 is our smallest value, and we continue on from there. Yeah. The way the equation is written gives it away. So the A, normally we have y equals, so it's P equals, so the P is in the place of where the y is, and the A is where the x normally is. Yep, so dependent and independent variables, we call those. Next, Tom. Part C. We're not done with this question yet. A larger building has an area, so A again, of 668 metres squared to be painted. How many litres of paint will this require? Now we now have an equation. This is the one that I've put in the box. All I need to do is sub that A value into it. P is going to equal 1 over 12 times by the area that I've been given, 668. That equals 55 2/3 litre. Keeping it exact for now. Part D, a paint supplier sells 40 litre buckets and 4 litre tins, of paint. How many buckets and tins must be bought in order for the paint to paint the building completely? All right, so we need 55 2/3 litres. Hopefully you can see we only need one 40 litre bucket. Okay? We're a lot of waste. We're trying to minimise our waste. We'll take one 40 litre bucket. if I take 40 litres out of my 55 2/3, there's going to be 15 2/3 litres left, and I want to see how many 4-litre tins I'm going to need. So I divide that by 4. There's 4-litre tins, they said, so it's 3.9. You cannot buy 0.9 of a tin, so you would always round that up, saying that you would need 4 tins of paint. So to write that out, you would say, therefore, I need 1 40-litre bucket and 4 4-litre tins of paint. And that's if you manage not to waste anything, which never happens. But we don't worry about the... That's true, yeah. 100 mils, that's not very much. The roller will probably suck that up. Anyway. Question 4, next page. The owner of the FizzGig manufacturing company uses a uniformly elastic demand curve to model their sales. Thus, if the price of a FizzGig is P and the quantity sold per year is Q, then the turnover from sales is constant. It is giving me equation. It says that is PQ is equal to T. And although we've been using K as our constant, they're saying we want to use T as our constant for some reason. They want to change the letters around to try and confuse people, catch people out. Not going to happen to you. Not going to happen to you. So we've been given the equation that we're going to work with. Part A says last year the price of a FizzGig was P equals $6 and the quantity sold was 400,000. Find T. Okay, similar to what we did in the last question, we can sub those values in to the equation that we've been given and find T. So that will be PQ, so P was 6, Q was 400,000 equals T. So when you times those together, yeah, you get 2,400,000. That's our constant. The company's board of directors, actually, it just said to find T. I kind of want the equation though. It's going to help us later on. Our equation, I'm going to do that underneath. That means our equation is going to be PQ equals 2,400,000. That was the answer we actually wanted, but we need that equation to keep going. So I'm going to write that there as well.
Oh, I was like the 2 and 4 was so close together.
Yeah, it's a very messy 4. I'll write it neater. Try to write it neater. There you go. The company's... It's not any better?
No.
What's wrong with my writing?
No, it's just the 2 and the 4 are closer together than the...
Oh, okay, sorry. I see what you're saying. No, 2,400,000. The company's board of directors wanted to raise the price to be $8 next year. Now, because we've been given a relationship between the P and the Q, naturally you would think if people in the shops are going to raise their prices, they might sell less of them. You make something cheaper, you sell more of it. So how is that going to affect the number of FizzGigs that they expect to sell now? Using that equation, our price has changed to 8. So that's 8 for the P. Q is the quantity. We're trying to find out what quantity we're going to sell now. And that is equal to the 2 million. Let's see if I can write them closer together for you this time. How's that? Is that better? Thank you. Oh, dashes. Then we divide the 8 out of that, which means they're only going to sell 300,000 FizzGigs if they raise their price. FizzGigs sold. I made up something. Under this model, girls, boys, everyone's waiting for you to finish your conversation, so Under this model, what will happen to the sales if the price is doubled instead?
Is that double
So,
6 or double 8?
This, according to this model, if you made it free, there would be infinite people buying.
no, because there's an asymptote there, unfortunately. Because this actually is a hyperbola. So there's an asymptote. You can't make it 0. So our starting price was 6. It was suggested, they said, we want to raise it to 8. But they said instead we're going to double. So it's the 6 that we're doubling, okay, not the 8. So we're doubling our price now to be 12. So it's going to be 12Q is equal to the 2,400,000. Dividing the 12 means that they're only going to sell 200,000 fizz gigs. A made up thing. Sketch the graph of the demand curve with Q, it's telling you here, Annabelle, it's telling you Q on the horizontal axis and P on the vertical axis. We're not going to have any negative values again here. We can't sell a negative amount of things. So Q on the horizontal, it tells me, and P on the vertical. Now we were given, we don't need to sub in points here. Year 11, stop talking. We've already worked out some information that we can use to plot this. So we know what was happening at P is 6, 8 and 12. Okay, so they were P values, and we know the corresponding Q values that those had. And we had Q values, I'm looking back at my notes here, was from 200,000, 300,000 and 400,000, looking back through A, B and C from up above, right? So across the bottom here, we're going to have to go up by 100,000s. So I'm going to go 100,000, 200,000, 300,000 and 400,000. No, not. Did I write million? No, I've got. No, that's when you times them together that made the 2,400,000. But the Q values, or I'll shrink my screen down. So the P values I had were 6, which get 6 and that one. I had 8 and that one, 12 and that one. Okay, so they're the values that we're going to be able to plot on here. The Q values, as I said before, go up to 12. So given we've got limited space here, how about we go up by 2s? 2, 4, 6, 8, 10, 12. So from A, we were told that P is 6 and Q was 400,000. So P 6, Q 400,000 would be a dot over here. From B, we had P equals 8, and that gave us a Q of 300,000, which is there. For part C, we had P equals 12, and that gave us Q equals 200,000. Now, this is not a straight line, okay? Even though I've got quite a big scale happening there, this is actually a hyperbola graph, because looking back at that equation, the PT equals T, when you're timesing your XY together and have a constant, that is your hyperbola graph. So we're going to make sure this looks like it's curving around like that. Ben.
I figured out the equation for a square.
That's lovely.
I don't really care.